In this video, I'm going to be breaking down how to solve problems involving two blocks connected with a rope like it's nothing. We're going to start with the simple question here. And as I read it, I'm going to draw a diagram. So two blocks, mass 1 and mass 2. Mass 1, mass 2 are connected by a light rope on a smooth horizontal surface. When a physics question says smooth surface, that just means there's no friction. That's just something to keep in mind. A horizontal force of 20 newtons is applied to mass 2, so assuming to the right. And the question's asking us to find the acceleration of the system and the tension in the rope. Now, when it comes to these type of problems, tension usually reveals itself naturally after finding acceleration. So let's focus on this first. I like to list out exactly what we know. So we know mass 1 is equal to 3 kilos. Mass 2 is 2 kilos. The force being applied is 20 newtons. Let's say in the positive x direction. And we're looking for acceleration and tension. We can easily find acceleration using Newton's second law. So Newton's second law is F equals ma. Rearrange it for acceleration. A equals F over m. And acceleration throughout the system is actually the same. So acceleration for mass 2 is the same for mass 1. Because if we start dragging mass 2 forward, then mass 1 is going to follow at the same speed. They're connected by the rope. That means when we consider the mass in this equation, we have to consider the total combined mass, which would be m1 plus m2. If we were looking at one block only and they had different acceleration values, then we wouldn't do this. Now we can plug our values. So F is 20 newtons divided by mass 1 plus mass 2, which is 3 plus 2, aka 5, giving us 4 meters per second squared acceleration. Now let's keep this in mind because we're going to need acceleration in order to solve for tension. Before we solve the tension, I have to explain to you an important concept. When the question explicitly states that the rope or the string is light or massless and the mass is negligible, that means that tension, the force, is equal throughout. So at every point, tension is the same on the rope. What that means for us is that the tension pulling on mass 1 here is the exact same strength as the tension pulling from mass 2. There is only one tension value, which makes our life easier. Since tension is a force, we're going to be using Newton's second law. And we can choose any block we want to find tension. Let's isolate and examine mass 1, because mass 1 is a little bit simpler. What are the forces acting on mass 1? There's only tension. That's the only one we care about. So tension equals ma. And we can actually just plug in our values and straight up find tension. So mass is 3. And acceleration we just found as 4. Giving us 12 newtons of tension. That means as our system gets pulled with 20 newtons of force, it accelerates this fast and mass 1 is pulled forward with this much force, 12 newtons. Here's the second problem for today. And I'm going to give you a chance to pause the video and try it yourself. So now I'll go through the solution. Let's draw a diagram again. So we have two blocks, mass 1, and we have mass 2. They are 3 kilos and 2 kilos respectively, connected by rope on a horizontal surface again. The coefficient of kinetic friction between each block and the surface is 0.2. What does that mean? That means as we try and slide forward, kinetic friction will appear and oppose our motion. And the coefficient, represented with this symbol, is 0.20. A horizontal force of 20 newtons is applied to mass 2. So that would be this way. We have to find, again, the acceleration and the tension in the rope. This is very, very similar to the last problem. And I did that on purpose, but I threw in friction. So again, let's list out what we know. We know mass 1, 3 kilos. Mass 2, 2 kilos. The force being applied is 20 newtons. And we also have to remember this constant. Gravity is 9.8. Acceleration is found again with Newton's second law. But it's a little bit trickier. So again, we're going to be looking at the combined masses, which is mass 1 plus mass 2. But the net force acting on this system is a little bit different. Instead of just being straight up 20 newtons like it was last time, it's this forward force, so we can call that F. It's subtracted by friction because friction is opposing us, so we minus. So friction would be friction of the second block and friction of the first block. That is the net force acting on our system. So we have to take into account friction this time. Now, what is friction? How do we find friction? The kinetic friction formula is coefficient, which is up here, multiplied by what's called the normal force. Now, the normal force is simply equal to the weight of the object because there is no vertical motion happening. Just keep that in mind. Let's compute kinetic friction for both of our objects because they're going to be slightly different since they have different masses. For mass 1, it would be 0.2 times the mass of mass 1, which is 3, times gravity, 9.8. This gives us an answer of 5.88 newtons. That's the friction opposing our motion when mass 1 rubs on the surface. And we do the exact same thing for mass 2. We just plug in our numbers. So 0.2 multiplied by the mass, so 2 kilos, 9.8. The friction here is 3.92 newtons. Let me recap what we've done. So we wrote our formula, but we realized that we need to find the friction values. We plugged in our numbers into the friction formula. And now we are ready to solve for acceleration. I'll just quickly substitute in our numbers. And acceleration comes out to be roughly 2 meters per second squared after you put this into a calculator. That's it for acceleration. And after we find acceleration, we are able to find tension. Now let's solve for tension. Using Newton's second law, we can list out the net forces acting on whatever block we want. Because again, tension is the same for both of the blocks. So let's choose the second mass. What forces are acting on mass 2? Well, we have the force pulling it, so F, and subtracting it is tension going in the opposite direction, and also friction. This is equal to MA, specifically M2A. Rearrange for tension, you get tension equals F minus F2 minus M2A. Now, we simply plug in our numbers, and I'm not going to do that on screen, but we get 12 newtons of tension. And yes, that does match up with problem 1. This is problem 3. 2 blocks, mass 1 and mass 2 are connected by a rope, and the coefficient of kinetic friction is 0.25. Horizontal force is applied to mass 2 like that, so that the system accelerates at exactly 1.5 meters per second squared. So if you notice, we're not given a force here. Instead, we're given the acceleration. We have to find the force and, by extension, the tension within the rope. Let's list out what we know. So mass 1 is 5 kilos. Mass 2 is 3 kilos. We know gravity is 9.8. And we are looking for force and tension. So instinct says solve for force with Newton's second law, right? But here's the problem. Newton's second law and the numbers we're given would give us the force for the entire system, but that would take into account the force of friction on the blocks. We don't care about that. We only want this force, right? So that's not an approach that we can take. We have to first find tension. Now, tension is very easy to solve when you already have acceleration. But here's the problem. Tension is affected by all the forces acting on our thing. That's how Newton's second law works, right? Net force. So that means we're going to have to find the frictions on our masses. Luckily, that's easy for us. It's simply the coefficient multiplied by mass multiplied by gravity. I'm going to skip the solving because we've seen this before. The friction of the first object is 12.25 newtons. That is this force here. For the second object, it is 7.35 newtons. That is this force here. Now, let's find tension by writing a Newton's second law equation for mass 1, just like we did in the previous problems. So let me ask you, what forces are acting on mass 1? Well, there's tension, and tension is being opposed by this force here, that being friction. And this is equal to M1A. This is our tension equation based on the forces and taken from Newton's second law. Let's rearrange by moving this to the other side. You get tension equals friction plus MA. Now we simply plug in our values. So we have friction 1 and we can plug that in, plus mass 1, which is 5, times acceleration, which we were given at the start, 1.5. We find that tension is equal to 19.8 newtons. And finding tension was extremely important because now we can find force. We can apply Newton's second law on mass 2 as an isolated system. Why do we do this? Well, we're looking for this force here, right? And we can't find that looking at mass 1 because this force is not involved in mass 1. So it won't be in the equation of mass 1. We can't look at that system wide because again, friction is muddling it up. So for a clean equation to find this force here, we can just isolate this mass 2 system. So what are the forces acting on mass 2? Well, there's of course the unknown force that we're looking for. And going against that force, opposing it, is tension and friction. Simple. This is equal to MA. That is our crafted equation for mass 2. And we can go ahead and solve for F, giving us F equals M2A plus T plus FK2. I'm going to plug in my values very fast. This gives us a force of 31.6 newtons in the right direction. That means, physically, if we are accelerating at 1.5 meters per second squared, then the rope must carry this much newtons and we are getting pulled forward with this much force. Now, this is the second last problem we're going to look at today. And if you want to try on your own, give it a good attempt. It's a little bit more tricky than the previous problems. And now I'll solve it. So we have two blocks, mass 1, rope, and mass 2. Now here's what's special about this problem. This time it's static friction. In case you need a quick refresher, static friction is the friction that's present when you try to get something to start moving. So you push and you push and you push, and when it finally breaks and starts to slide, kinetic friction takes over. So usually static friction is going to be stronger because it's harder to get something to start moving than it is to keep it moving. Anyway, the coefficient of this is the same symbol, and it's 0.30. There's a horizontal force applied to mass 2. We don't know what it is. This is a limiting constraint problem. And if you have exams, they're going to love doing this kind of stuff. We have to find the minimum force required to just start the pair moving. And I'll give you a tip. When questions ask for the minimum, you just find the minimum. What is that minimum? Of course, before we do that, let's list out what we know. I'll do this very quickly. So how do we even approach something like this? How do we find the minimum force? The minimum force required to start the blocks moving would be a point where we're pushing with enough force to match the static friction that's opposing us. Because with static friction, the harder you push, the bigger it gets. And then once you reach a certain threshold, you are able to overpower it and start moving. What does that mean? Let's say the static friction force is 0 when no one's touching the object. As you push, maybe it rises and rises and rises. You push hard and harder, maybe it hits like 30 newtons. And then that's the maximum. There's always a maximum. Once you push hard enough, let's say you push 50 newtons of force. Well, you broke free of static friction. We have to reach the point where our force is exactly equal to static friction. Why? Because that would be the bare minimum. If you went any stronger than that, your force went up by any value, then you would start moving. And by the way, since we're looking for the threshold, we're not quite moving yet. If force is equal to static friction, we're just about to start moving, but our object is going to be at rest still. What that means is acceleration is actually going to be 0. And if acceleration is 0, we know from Newton's law, by extension, net force is also equal to 0. You'll see why this matters soon. So let's write our equations. First, I like to solve for the static friction values. It just helps to have them. So the static friction formula is very similar to the kinetic one. It's the coefficient multiplied by the normal force, or mg. If we apply this to both of these masses, 5 and 4, we get these values. So the static friction of mass 1 is 14.7 newtons before it starts moving. And the static friction maximum of mass 2 is 11.8 newtons roughly. Notice how it's a smaller value because it's a lighter object. Now, we can use Newton's second law across the whole system to find the minimum force required to start them moving. Why do we look at the whole system? Because remember, this force dragging us forward, whatever this force is, makes the object behind it move at the same speed as this one. Because they're connected, acceleration would be constant. But actually, because we're looking at the specific circumstance where static friction and the force balance and the net force is 0, then acceleration is 0 as well. What am I talking about? Well, look at Newton's second law. F equals ma. Let's write out what's F. What's the net forces on our system as a whole? Well, there would be the force pulling us forward, which is what we're looking for. And opposing that, there is the two friction values that we just found. So static friction 1 and static friction 2, right? That's every force moving along the horizontal plane. This is equal to ma, according to Newton's second law. But since a is 0, this is equal to 0. It's a little bit tricky, but just follow along and the math will clear up. We can isolate for force because that's what we're looking for, right? We get F equals the frictions added together. That is 14.7 plus 11.8. That is 26.5 newtons. That is the threshold of force. So if you go anywhere over this number, your chain will start to move. So that's force, 26.5. That's done. What about tension? Again, we're looking at it at the threshold. So that would be when A is 0, net force is 0. Same thing as always. Let's examine one part of the system in isolation, specifically mass 2. And we're going to write a Newton's law equation for it. We have the force going to the right, subtracting tension and static friction, equals m2a. And remember, acceleration is 0. So this whole thing is 0. If we isolate tension, rearrange our equation, we get T equals the force minus the static friction. Finally, we can plug in our final values. So 26.5 minus static friction number 2, because we're looking at mass 2. So 11.8, giving us 14.7 newtons of tension. That is this problem solved. That is how you solve a limiting case or a threshold type problem. I'll just quickly recap the thinking strategy. You have to think about what conditions that threshold is and what different variables are at that threshold. It takes a little bit of practice and you have to recognize some patterns. For example, we know that the net force is 0 because the acceleration is 0. That carried us through the whole problem. And we knew that, well, the overall force would have to match the static frictions of our system and then go beyond that to start moving by logic. So understand your concepts, learn your stuff, and we're going to move on to the final problem now. This is a big problem, and I'm going to walk you through it. But we have a lot of stuff going on. Like always, I'm going to list out what we know. So we have 2 blocks, and I'm actually not going to draw a diagram this time. We have mass 1 as 6, mass 2 as 4. The static friction coefficient is 0.3. By the way, I'll underline where I'm getting these numbers. And for kinetic friction, it is 0.2. There is a horizontal force that is applied onto mass 2. And that's what we're going to start to find. Honorable mention, gravity, 9.8. And we also don't know tension. This is going to be difficult. Let's find the minimum force required to start moving our 2 blocks forward. We're going to call this force F min. Min for minimum. We're going to use the exact same approach as we did in the previous problem because it's pretty much the same thing. The minimum force thing. So we can actually skip a lot of steps and we can steal the equation, which was the pulling force at the threshold minus the 2 frictions of our objects. If you don't remember why we did this, remember acceleration is 0. This is taken from Newton's second law's net force section. And that gives us this equation here. From that, we are able to isolate this value. So the minimum force required is equal to the frictions added up. And I'm going to write them in equation form. So friction 1 plus friction 2. Substitute in our values. So US is 0.3. M1 is 6. 9.8. And then the exact same thing, but 4 kilos instead. That means that the minimum force required is 29.4 newtons. And if we go above that, in any capacity, we will start moving. Notice how we did pretty much the exact same thing as the previous problem, but I did skip a few steps because we've seen how the process goes. So that's done. Now for part B of the problem. If the applied force in our block is 40 newtons, what is the acceleration of the system? So we're looking for acceleration now, and the tension. As we've seen through this video, if we find acceleration, tension will be easy. Acceleration can be found with the net force of the system divided by the combined mass of the system. Now the net force is interesting here. So it's 40 newtons, of course, but it's not static friction this time. We've been working a lot with static friction in the last two problems. This time it's kinetic friction. Why? Because we're already moving. 40 newtons is larger than the 29 newton threshold, which means that we are already sliding. If we are already sliding, kinetic friction is taking place, not static. The kinetic friction formula is this. I'm just going to skip the solving here. I'll give you the straight up number values. So the kinetic friction of mass 1 is 11.8 and the kinetic friction of mass 2 is 7.84. That is the net force acting in the horizontal plane, and the combined mass is simply 6 plus 4, so 10. That gives us an acceleration value of 2 meters per second squared. Perfect. Now that we have acceleration, we can attempt to find tension, which is the second thing that this part of the question asks us for. Let's simply examine mass 1. So I didn't draw a diagram because if you can work with numbers alone, it is a good skill to have. We've got tension, and opposing tension is kinetic friction. This means if we write a Newton's second law equation for this, we get T minus friction equals MA. We can easily solve this now. So rearrange, we get tension equals Fk plus M1A. Substitute our values. So 11.76 plus mass 1 times acceleration. And tension is 24 newtons. If you're wondering why I went over tension so quickly this time, because we've solved for tension in every single problem, I believe. It's the same process. You just make a Newton's second law equation and then isolate for tension. That's 24 newtons. Now it's time for the final part of the problem, problem C. We have to calculate the force that's required to keep the pair of blocks moving at a constant speed if they are already sliding. Constant speed is the same as saying no net force. So zero net force, because constant speed means no acceleration. These things go hand in hand. Then we can write this equation. The force required to keep the blocks at a constant speed, let's call this Fc, minus the friction forces, and it's kinetic because it's already moving, is equal to 0. This is familiar, isn't it? We did this in part A and in the previous problem. All we have to do now is isolate Fc, and if you're a little bit lost, this comes from, again, Newton's second law. Now, plug in our values, get Fc equals 11.76 plus 7.84, giving us 19.6 newtons, which might trigger a red flag for you. You might think 19.6 newtons, that's less than our threshold. How are we moving? Well, that's exactly correct. This is normal, because once you're already sliding, it's easier and it requires less force to keep sliding. So the math checks out. That is the final problem. And I've created 3 cheat sheets for every single topic in physics. I use them myself. They're designed for quick answers. Just join the Discord down below. It's free. You can talk to other people, ask me for help. I'm active as well. It's completely new. Go check it out.